Hello all. In this video, let's take a look at TurboQuant. So this is a recent research paper that is released by Google in ICLR 2026, and let's see how Google compressed a memory 6 times without losing anything. So as we know, there's been quite a crisis happening inside every LLM that we use right now. So the models are getting smarter, but they are also getting hungrier. So every token that you generate costs memory, and that memory is becoming a bottleneck. So Google published this elegant solution, and let's understand it from the first principles. So spoiler alert, TurboQuant is a vector quantization algorithm where it takes a vector of numbers and then it converts that into another vector of numbers, but this takes up less memory when compared to the original vector without losing accuracy. So let's see how Google achieved that. Before we get into TurboQuant itself, let's make sure that we're all speaking the same language. So there are 7 foundational concepts that everything else depends on. So let's talk about these 7 concepts first, but each one is quick. So if you have already know this, just take a sit back before we dive deep into the TurboQuant algorithm. So now let's proceed towards our first concept, that is tokens and context. So what is a token? LLM don't read words, they read tokens. So for example, consider this TurboQuant. Now this might be 2 or 3 words, right? Or else consider that this sentence, what is the capital of France, right? So each of this word can be considered as a token. So this is how LLM reads words. Now second thing is context. So context means every token that the model has seen in your conversation so far comes under context. The model takes a look at all the previous tokens and not just the last one. So to simplify this, let's say in your turn one, this is your input, this is your user message, and this is the text response, right? So in the second turn, so the response that gets generated also goes into the context. So if you see in turn 2, this user message is there, this text response is there, and the new question that you ask in turn 2. So all these three things go as an input, and there will be an output. So all these recurring user messages, the response from LLM, all these things go under LLM context. So whenever in, let's say in turn 3, a new question gets asked, so it takes a look at all the previous messages and then answers your question. So this is what context means. Now coming back to the context length, so longer context means the model can remember much and more, right? So let's say in the latest release of Cloud Opus 4.6, they say that the model has a context length of 1 million tokens. That means it can store a lot of previous conversations that are happened, so that it will be able to generate much better responses. This is what context length means. But the downside of context length means that the model has to process more and more tokens for each and every new word it generates, and this becomes expensive. Now, the final concept that you have to understand is vector. So, vector is how the model stores each token's meaning. So, let's say capital. This gets converted into a vector like this. So, this is how the model stores the tokens. So, when we say TurboQuant, that means it is doing an operation which takes this vector and then converts into a compressed vector. So, we'll see how does this algorithm takes a vector and then converts into this compressed vector, but without losing any accuracies. So now let's take a look at precision and bits. So when we say 16-bit, that means each number in the model is stored using 16 binary digits. So 16 ones and then 16 zeros. So more bits means more decimal places. That means more precision, but also results in more memory. So 32-bit is called as a full precision. That means it takes 4 bytes per number. So this is what all the traditional software uses. And then 16-bit converts that into half. That is the standard for all the AI models that we see today. And finally, 3-bit. This is what TurboQuant does. So it uses about 1/10 of the memory of the 32-bit, right? So think it of like a decimal places. Like 32-bit is something like 3.14 or something, etc. So see the precision. When we store it as a 16-bit, that means we are rounding off a few digits, right? So see how the precision is being decreased. Now 3-bit means we are just storing as 3.1. So lesser precision means smaller file and less memories. So for example, if you do a simple math, a model with 1 billion numbers at 16-bit will be 2 GB, right? But whereas the same model at 3-bit will be 0.37 gigs. So we are reaching the same quality but with 5x less memory. So now let's proceed with the third concept, that is the KV cache. So let's understand how LLMs generate text, right? So LLMs generate text one token at a time. So to pick the next token, the model runs something called as attention. So it means that it takes the current token and then it compares to every single previous token to decides what's relevant. So let's say you said something like, so I love dog, right? And after that you have asked many questions, and then let's say after some point of time you ask, so what is the animal that I said I liked before, right? So to generate the response for this, LLM takes a look at all the previous tokens and then it does something called as attention. So by doing this attention mechanism, it understands that this conversation or this token is relevant to what it wants to generate the next. So in simple, this is what attention means. So it compares the current token to every single previous token to decide what's relevant. So in this example, when you ask what is the animal that I said to you earlier, so it takes a look at all the previous tokens that it has been generating so far, and then it does this attention mechanism and then it compares this. So by comparison it understands that okay, this is something that is relevant to the question that is coming right now. So this is how LLM generate text. So now what is KV cache? So as I said, for every question it will take a look at all the previous tokens, right? So to avoid recomputing those comparisons from scratch every time, so the model stores something called as a key and value vector for each and every past token. So this is stored in something called as a KV cache. So these comparisons that we do for every other question, let's say if there is another new question that you ask right now, it does the same comparison again and again with the previous token. So to avoid these repeated conversations, we store in something called as a KV cache. So the problem here is, as the KV cache grows with each and every generated token, that means it stores a massive cache, right? So our long conversation means massive KV cache. So at 16-bit precision, a 100K token context can consume approximately 50 to 100 gigs of GPU memory. And this is what TurboQuant is trying to solve. So it tries to compress each key and value vector in the cache from 16-bit to 3-bit, right? So but thereby we are saving approximately 5 times the memory without losing the quality. So coming to the next concept, that is attention. I know we briefly discussed this concept earlier, but let's make this quick. So let's say that when you read, the animal didn't cross the street because it was too tired. So we instantly know that it refers to animal, not the street. So you are doing something called as attention, where you are linking a word back to the most relevant earlier word, right? So this is what model also does. For every new token, the model computes a similarity score against every past token. So high score means it thinks like pay attention here, whereas low score means ignore this. So this final output blends past tokens weighted by a scores. For example, consider this sentence where the cat sat on the mat because it was soft. So here when we take it word and then do this similarity score against all the tokens that it saw, the score for mat will be high. We know that how much attention it pays to the previous word. So the model figures out that it is equal to mat because mat gets the highest score. So now why is this expensive? With 100K tokens, each token must compute 100K similarity scores, and this happens for each and every attention head in every layer. So that means there are billions of comparisons per token generated. Now, one key connection is when we say a similarity score is computed between this and this, these similarity scores are computed using dot products of the key and query vectors. So, which is exactly what the KV cache stores and what TurboQuant compresses. So now let's proceed towards our next concept, that is dimension. Let's understand what is a dimension first. Dimension is just an axis. Let's say a point on a map has two dimensions, right? X comma y. Similarly, a point in a room has three dimensions, right? So we can represent a point in a room something like X, Y, and Z. So similarly, a token vector in an LLM has 4096 dimensions. Now 4096 dimensions is not a fixed number. It depends on the model. For example, GPT-2 has something somewhere around 768 dimensions, whereas Llama 2 has 4096 dimensions. So what are 4096 dimensions and why do we need so many dimensions? More dimensions means more nuance, right? A 2D vector can encode something like a positive or negative sentiment, but as a 4096 dimension vector can encode grammar, topic, you know, tone, formality. So let's take this example. So let's say dimension 0, we can measure how positive the sentiment is. Dimension 1, somewhere it encodes how formal the language is, whereas in dimension 3 it says whether it is present or past tense. So more dimensions means we can encode more information. So one thing to note is no humans assigned these meanings, right? So the model learned this from the data. So each dimension captures something the model found useful during training. And now the concept of dot product. So earlier we were talking that LLMs do something called as an attention, right, where it compares the query to all the previous tokens it sees and computes something kind of a similarity score. So this score is nothing but a dot product between these two vectors, that is the query vector and each and every key vector that it saw in the past. So higher dot product means that it has to pay more attention to that token. So what is a dot product in simple? That means we take two vectors and then we multiply each pair of matching numbers. So for example, take this query and take this key. So when we dot product, this results in a score of 12. That means this is a high score and these tokens are related. So in 1496 dimension, this means you multiply 4096 pairs and then sum them up. This tells the model how much one token should attend to other. So moving to the final concept, that is GPU memory versus regular RAM. When people say AI needs a lot of memory, they don't mean the RAM in your laptop. They mean GPU VRAM. So let's take the top of a line NVIDIA H100 GPU. Now that has 80 GB of VRAM, but it costs around $30,000 per card. So the model weights, the KV cache, all the intermediate computations must fit in this 80 GB VRAM. So you can spill out to regular RAM, but the thing is it is too slow. The GPU would spend more time waiting for data than the computing. So take an example, Llama 3B 70 billion parameter model at 16-bit already needs 140 gigs just for its weights. So that means it needs more than one GPU. Now to that add a long KV cache and then you are looking at 4 to 8 GPUs per serving instance. So let's say if we compress the KV cache 6 times using TurboQuant, you might go from needing 4 GPUs to 1. Okay, so now that we have covered the foundational concepts, let's move on to the next thing. That is, let's see what is a memory bottleneck. We saw that the KV cache grows with each and every token, right? So let's say whenever you ask a new question, it does something called as a attention thing where it has to calculate the similarity scores between each and every past token to the current query, right? Now this computations, as I said earlier, we store them in a KV cache so that we don't have to recompute this again and again and again. So let's say for each token generated, the model stores key and value vectors it in a KV cache. Now a 100K token context at a 16-bit precision can consume 50 to 100 gigs of memory. So here if you see, memory is the bottleneck, not the compute. So attention computation requires repeated reads of the entire cache. So it has to read the entire cache, right? So here memory becomes the bottleneck, not the compute. So finally, what we are trying to achieve using this algorithm is we are trying to compress this KV cache. So the place where we store all the previous computations, we are trying to reduce that memory taken by the KV cache. So in simple layman terms, if you want to understand KV cache, consider it as a high speed cheat sheet where it stores each and every token's context so that the model never has to recompute it again and again, so that it can use it for fast inference. So how do we reduce the size of a KV cache? Through quantization. So let's take a look at quantization. So let's say we store the numbers with less precision, right? So what could go wrong there? So let's say before quantization, as we saw earlier, that let's say this is how the vector looks like. So 32-bit float and 4 bytes per value. So let's say we quantize. So after quantization, let's say we do a 3-bit quantization. So if you see the precision of these dimensions, it has reduced, right? So for example, from 0.2374623, it got reduced to 0.237, right? That means after quantization this is 10 times smaller, but it also has some tiny error because we are reducing the precision, right? So it has a tiny error. Now for a normal vector, this works out beautifully, like 10 times compression, faster reads, no retraining required. But there's a catch here. Real LLM vectors aren't normal. They don't look like this. For example, if you take a look at a real LLM activation vector, so you'll see like this, right? So we already saw that dimension 0, 1, 2, 3, right? But if you see in this vector, we see that there is one dimension where it caused massive activation. This is also called as attention sink. Now I can attach an article below to the video where it explains why do we see such massive activations. But this scenario where we see such massive activations is normal in a LLM activation vector. So if we try to quantize this vector, we can see on the right side that we snapped the dimension 1, right? We made the dimension 1 to 1 and then rest of the dimensions to 0. So this means a vector gets snapped into its cardinal direction and all the semantic content is being destroyed. So what did we lose here? A cardinal direction like 0, 1, 0, 0 only tells you which dimension is active, but the rest of the information we are losing. But this is a general phenomena where we see with LLMs. So a real LLM activation vector would look something like this, where one dimensional would be causing massive activation, but after we do some naive quantization, there is this dimension just snaps to a cardinal direction and all the semantic content that this vector carries will get destroyed. So this is our enemy, that is the massive activations. Okay, so now let's see how should we tackle such activation vectors where we see massive activations, right? What if we rotated the vector first, right? Let's see what does rotation mean. So let's say you have a vector that looks something like this, right? So 0.000 and then 1, right? So the dimension 0 means nothing, whereas dimension 1 has a higher activation, right? That is 1. So this is what we saw earlier. So let's say you rotate it. Let's say you rotate it at somewhere around 45 degrees. That is the diagonal direction. So after you rotate at 45 degrees, there will be changes to a dimension, right? So now the dimension 0 would look something like 0.707, and dimension 1 would also rotate like 0.707. So if you quantize, it's like 0.7 comma 0 comma 7. If you want to dequantize, that means if you want to go from this quantized vector back to a dequantized, so you have to counter rotate by 45 degrees, right? So 0 comma 1, when we rotated 45 degrees, it resulted in this vector that you see on the right side. So if you want to go back, you have to requantize as the same. So now the key thing to note in this rotate a vector is when you take a high dimensional space, it's the same operation just described by a matrix instead of a single angle. So the key property is the rotation always preserves the length. The total information in that vector remains unchanged. So what changes is what dimensions carry the weight, right? So before, if you see dimension 1 almost has everything, right? But after a random 45-degree rotation, now both dimensions, if you see dimension 0 and dimension 1, they share equally. So now when you quantize, you shave off decimal places. So both dimensions get a small proportional rounding error. So it is not a catastrophic snap that we saw earlier where one dimension snaps to one, right? And so when you want to dequantize it, you just counter rotate on the way out and you almost recover everything exactly like the original. So here, one thing to note is random just means the angle is chosen randomly, so you don't need to train that angle or you don't need to tune it also. So any rotation works because all rotations preserve the length. Now let's apply this rotation concept to a real vector that we saw earlier. So let's say this is your original vector, right? If you can see that there is one dimension that caused massive activation, we also call this as a quasi sparse vector. Or when you randomly rotate, you see that the weight is distributed evenly, right? So now you quantize it. So now after quantization, like 0.24 becomes 0.2, etc., right? So we are just losing the precision loss, but we are not going to a complete collapse. So now when you want to dequantize it, as I said earlier, you just have to counter rotate to recover. So before we proceed with TurboQuant's contribution, let's take a step back and see why does a random rotation work, right? If you see, before rotation, there is one dimension that is enormous, right? So everything else is zero, but there is one dimension where it's like 0.99. So after rotation, the same total energy now is spread across all the dimensions, right? There is no single dimension that dominates. So quantization now causes proportional precision loss, not just a collapse. Earlier, if you do a quantization for this vector, we are snapping this to one and rest of it are being collapsed, right? But now because this total energy is spread across different dimensions, we are just losing a precision across each and every dimension, but we are not just completely collapsing. So the reason why this is working is because of pure geometry. If you do any random rotation, so it will land somewhere where the weight is being distributed evenly. So if we keep on increasing the dimensions like 4006 dimensions, now this effect becomes more and more pronounced. So the TurboQuant paper proves the same thing mathematically, and it gives exact distribution bound. But the overall intuition of random rotation is straightforward. So now that we have learned why random rotation works, let's move on to the next concept, that is the calibration problem. So let's take a quick recap. So we have seen that we have started with a vector and we tried to quantize it, but when we take a real LLM vector, we found that there are many cases where there is one dimension that shoots up, right? So if we quantize such a vector, we are losing a lot of information. So what we did is we rotated the vector, right? So if you see, so this is the vector that comes after rotation. So now if you take this rotated vector and you have to, quantize it. Let's take this aside. Let's see how we can quantize a vector like this, which comes after rotation, and how we can quantize that to 3-bit. So let's see the same example here. Let's say you have a number 0.724, right? So if you see 0.724, right? So let's say you have a number like that and you want to compress that into 3 bits. So 3 bits means 8 possible values, right? So as you know, just 1 bit means 2 power 1. That means 2 possible values 0 comma 1. Similarly, 2 bit means 0 0 0 1 1 0 1 1, right? So 4 values. So if 3 bit means that you can store only integers between 0 to 7. So how do you map 0.724 to 3 bits where you can only store 0 to 7? So for this to happen, you first need to understand the range of your vector. So this is our vector, right? 0.237, 724, 0.453 and 0.100. So you need to find the range. So range is nothing but the difference between min and max. So minimum is 0.724 and max is 0.100. So this is our range. Now you have to divide this range into 8 equal bins. Why do you have to divide into exactly 8? Because when you say 3 bits, you can only store integers between 0 to 7. So you have to divide it into 8 equal bins. Now if you divide it into 8 equal bins, this is how the intervals would look like. Now you take the given vector, that, and then see under what bin does this number fall into. So if you see 0.237 falls into bin 2, so like that 0.724 points to bin 7. So we convert each of this value and map it to a bin number. So it becomes 2750, right? So this is our input vector, right? So after we quantize this input vector into 3-bit, this is how it looks, 2750. Great, we have done the quantization part. Now as you can see, these are just a bin numbers. So in order to dequantize it, you need to know the minimum, you need to know the bin, and you also need to know the scale, right? So if you take the minimum 0.100 plus 2 into 0.89, that gives 0.278, right? So this is close to what we saw, right? So 0.237. So we took this minimum bin in scale. So if you take this bin number as 2 here, we got to 0.237, which is nothing but the original vector value which we came from. So we are successful in converting the bin numbers back to the original vector values. Now two things to note here. So let's say when we take an input query and quantize it to a 3-bit. Now again, in order to dequantize it, you need to know two things, right? You need to know the bin and you need to know the scale. So without this, the bins are meaningless. So if you don't have this information and you just have 2750, now you don't know how you can go back to the original vector, right? You don't know how to dequantize it. Now this phenomena is called as a calibration overhead. So two constants, right? So minimum and scale. These things should be stored at a full 16-bit precision. So why do you have to store at a full 16-bit precision? Because let's say if you go down and store a half-bit precision. So what happens is, even though if these numbers are slightly wrong, what happens is when we decode, right? So let's say if this minimum and scale, let's say if this precision is wrong, what happens is the original value gets changed, right? So then what happens, we are just losing the vector data. So why is this problem? Because let's say for our tiny 4 number block at 3-bit quantization is what we're doing, right? So 4 numbers into 3-bit means 12 bits, right? So data is 12-bit data. Now along with that, what are we storing? We have to store minimum and scale, right? So these two are constants and these two are 16 bits, so 32 bits. So total 44 bits, right? So of which 73% is just bookkeeping. So let's say when we converted this input vector and we quantized it into 2750, why did we quantize? We want to reduce the size. But if you see, after we did the quantization and calculated the memory which is taking, so the data part only takes 12 bit, right? The data part is only taking 12 bits, but whereas the calibration part is taking 32 bits. So calibration part is nothing but the minimum and scale that we require to dequantize it, right? So calibration part is eating up a lot of space. So 73% in, to be in precise, is what this calibration thing is taking. So we started with a goal where we wanted to compress from 64 bits, right? So 4 into 16 bits, right? So these are 4 values, right? 4 into 16 bits, and we wanted to compress this to 12 bits. How the 12 bits? 3 bits, right? 3 bit we are quantizing and into 4. So and into 4. So that means 12 bits. But you actually end up at 44 bits because of the calibration tags. So your 3-bit quantization is effectively 11 bits per number. Even though we are trying to quantize a vector from, let's say, 64 bit to 3 bit, which essentially should be only 12 bit, but because we have to store this minimum and scale, we are eating up a lot of memory. So we are not getting the benefit of 3-bit quantization, essentially because we have to store this calibration constants. So this is the calibration problem, and let's see how do we solve this calibration problem. How do we make sure that we can take something like this? So we can take something like this 2750, and then we can dequantize it to the original but without any calibration overheads. So that's our next step. Coming back to this slide, this is what exactly I'm saying. So we find the range. Once we have the range, we divide into bins, and then we take something like 0.237, and then and then see into what bin each of these values fall into. So 2750, right? So calibration constant, minimum and scale we have to store, and each of this is 16 bit each. So to decode it, let's say if you want to decode 2, that means you take 2, right, plus is equal to minimum, that is 0.100, plus bin into scale, that equal to 0.278, which is something close to our original vector. So now that we have understood the calibration problem, let's see how we can solve this calibration problem. So we use something called as a PolarQuant, also known as a polar coordinate. So we convert this vector that we got after random rotation into polar coordinates. So let's see how we do that separately. So let's see how does polar conversion work. So there are two ways to describe any point on a 2D plane. So first thing is a Cartesian and second thing is a polar. So you can say something like go 0.237 units east and 0.724 units north. So you can, that means you can write something as x comma y. But you can also tell the same thing but using polar coordinates. So how do we say that? You can say something like go 0.762 units in total but in a direction of 71.9 degrees. So here our notation is r comma theta. So if you see, both these describe the same point. One describes it as x comma y, whereas the other describes it as a radius and then the angle. So it's like it's just a different way of writing down its location. Let's say in simple terms, let's say if Cartesian is something like third house on the main street, polar is something like the house GPS coordinate, so 40.7 and something degrees. So it's just the same location, just the notation is being different between Cartesian and a polar. So how do we compute radius and angle? So let's take this x comma y 0.237 and 0.724, and then you have to compute the radius. So why did I take only these two? So you have to pair up coordinates. So in order to convert the vector to polar quant, you have to pair up as a coordinate. So take coordinates in pair and convert each pair to polar. So you take 0.237 and 724 as a pair, and then 0.543 and 0.100 as another pair. Now let's see for this pair, how did we come up with this r comma theta. So if you see the formula for r, that is the radius, is how far is the point from its origin. So let's say we have something like this, and this is our point. Then we have to see how far is this point from this origin, right? So how do we calculate that? It's nothing but the hypotenuse of the right angle. So if you do something like r is equal to square root of x square plus y square, and you get something like 0.762. So that means this point 0.237 and 0.724 is this units away from our origin. Right now, okay, we got to know that this is this much far away from origin, but we also have to know in what direction is it located, right? So for that, we also have a formula, like we do arc tan of y by x, and that gives 71.9. Think visually. So if you can draw an arrow from an origin to a point, right, this point, and the arrow would be 0.762 units long and pointing at 71.9 degrees. So we took the same thing and then we converted into polar coordinates. So how did we convert to polar coordinates? We have to pair up these coordinates, and then we have to convert them into r and theta. So r means it just gives how far away is this point from my origin, and two, at what direction. So if you take this example, so earlier we are saying something like go 3 east 4 north, right? But now we are saying go 5 units total but in 53 degrees angle. So it's just this exact same point, but only the notation is being different. So how does TurboQuant use this? So radius tells us how big the pair is, right? Whereas angle tells it the balance between the two numbers. Now after the random rotation, the angles always land in a predictable range, right? So if you randomly rotate, they always fall in a known range. So anywhere in between 0 to 90, they'll fall. By this I mean, since you already have the range, earlier if you see in the calibration problem, the missing part is the range, right? So you need to have an idea of a minimum, right? This comes from range. You need to have minimum and scale. But what happens once you have this polar quant is, when you convert into polar quant, the angles are always between 0 to 90 degrees, right? So always know the range for every block, for every input, for every model, no matter whatever it is, when we are converting into polar quants, you always lie in this predictable range. So minimum is always 0 degrees and scale is always 90 by 8. That is the our 3-bit quantization that gives 11.25. So here if you see, this is like a static value, right? So we already pre-computed that our minimum is always 0 and scale is always 11.25 degrees. So we don't have to store this again and again. So now using this, we can overcome the calibration problem that we saw earlier. So this is exactly what the slide says. So if we come back to slide and see, so finally when we store the result, we just store the quantized angles. That's all. So no minimum value, no scale factor, no calibration constants. Every single bit goes to the actual data. So let's say now when we store this as a quantized bins, let's say we get 6 and 1. I showed you how we get to this bins, right? So we calculate this range and etc. and see where do these two fall into, and they fall into bin 6 and 1. So each of this is 3 bits each, and if you want to dequantize it, what do? We just take bin into 90 by 8, that is 6 into 11.25 degrees, 67.5 degrees, which is close to what do we have here. So this is the magic of polar coordinates, right? So it's not about the math being elegant. So now when you say 3-bit quantization, you are actually getting the benefits of 3-bit quantization. So now let's recap the complete PolarQuant pipeline that we have seen so far. So first we do the random rotation. So why do we do random rotations? So that we don't fall into the massive activations of the LLM vectors that we saw earlier. Now what do we do to convert into polar coordinates? We pair, right? So we pair each of these vectors, quantize the angles, and then we only store them. So we don't store any overhead data. So traditionally, if you see, so once we quantized, we get 2750. Along with that, you have to store min, you have to store square. So that is 12 bits plus calibration 30 bits, that is 44. Now overhead is about 73% of a total storage. Now when you do PolarQuant, you just store 6 and 1. That's it. You don't need to store anything else. So that is 6 bits in total. That means 100% of your quantization goes to usage of actual data. PolarQuant makes use most of your bit budget, but it minimizes mean squared error, not the dot product accuracy. So we'll see how what does this mean in the next slide. Now there is another problem called as a bias problem. So we'll see what bias problem is. So so far we saw that the polar quant compresses well, right? So we can make use of most of our memory just to store the original data. But the problem with the polar quant is when we do this attention computations, right? So these scores become consistently wrong. So why? So let's take a quick recap of what attention does. So for each and every query, right, we take a query and we do a dot product into the past token that we have seen, and this gives us the attention score, right? So high score means LLM knows that it has to pay attention there, whereas low score means it will ignore that. Now what happens is, let's say when we compute the dot product of our query and each of our past seen tokens, let's say we got 12, 3.2, 11, and let's say this key is nothing but cat the set. So if you see from this computation, we can see that cat is the most relevant, right? But if you do the same with polar quant compressed keys, you can see that when you do query into key for cat, you'll get something like 13.8, 5.0, 13.3. When we use polar quant compressed keys, all these scores get shifted by some amount. It's also called as a systemic bias. You might be thinking that, so because all of this got shifted by same amount, now why don't they cancel out? So one thing is attention uses softmax. So what is softmax? It takes these values and converts them into probabilities where they lie between 0 to 1. But because softmax is non-linear, shifting all scores by plus 1.8 doesn't shift all the probabilities. It in fact distorts the distribution. That means low scores get boosted more than high scores. So now what happens is the model start paying attention to the wrong tokens. Let's say originally the model has to pay attention to the cat. Now it might be paying attention to the second word, that is the. What happens is over thousands of tokens, this drift kinds of accumulates over and over. So how do we make sure that we take this bias into consideration? So there is a technique for that, and it's called the one bit fix. So what do we do is we calculate the residual from the stage one. So when we subtract original key from the polar quant key, we get the residual errors. We can see here that, so this is our original key and this is our polar quant key, right? So if you subtract these two, then we can see what is the residual, right? So this is exactly what we are going to be doing. So we subtract these and get the residual. And how do we store this residual? So what do we do is we keep only the sign of each number. Let's say once we compute the residual of dimension 0, dimension 1, 2, 3, let's say this is our residual 0.032 and all these things, right? Now what do we store? We store only the sign of each number, right? 0 plus 1 minus 1 plus 1 minus 1, that's all. So we only store one bit per dimension, that is positive or negative, that's it. So our bias score that we got is 13.8, and the sign correction is nothing but minus 1.8, right? How do we compute? We compute it from the sign bits, right? Now the corrected score is 12.0. So just by storing one bit for every dimension, we are able to get the corrected score. So three important facts is, in order to eliminate the bias that we saw earlier, you have to store one bit per every dimension, which is of negligible cost. So this is why we see such a huge improvement on the TurboQuant. So now it's time for our end-to-end walkthrough. So we started with a vector that looks something like this. Now what do? We just rotate it randomly. So after rotation, let's say this vector looks something like this. So we take this rotated vector and then convert into polar coordinates. Now why do we convert into polar coordinates? Because if we directly take this rotated matrix and do a quantization of that, we are getting a problem where we have to store calibration constants. So to avoid that, we are converting it into a polar coordinates. So now that we have the polar coordinates, we just need to quantize the angles and store them. So for 71.9 degrees, it is sixth bin, and 10.4 degrees, it is the first bin. So we stored 3 bits into 2, that is 6 bits, and nothing on the calibration side. So when you want to dequantize it, it's the same formula, but you don't need to store anything. We get a vector after we dequantize in this step, right? So we calculate the residual between the original and our dequantized vector, and this is how our residual look like. Now what do? We just store the sign bits like +1, -1, +1, -1. We store them as a 4 bits per each dimension. And so finally, after quantization, our input vector would look something like 6, 1, 6, 1, plus, minus, plus, minus. So 6 and 1 are coming from the polar quants, as you see here, 6 and 1. And this plus, minus are coming from our QGL transformation. So totally 10 bits in total. So we started from an original 16 bit where it takes 64 bits of memory, but we achieved 6.4 times compression because finally we converted this 64 bits into 10 bits total. So finally, if we take a look at a full picture of a TurboQuant, we can say that it's a two-stage pipeline where we start with the input vector and then we convert them into polar quants. How do we convert? We rotate. We convert into pairs, then we convert into polar quant, and then we quantize the angles. And in the next step, what we do is we compute this residual that we got from the stage one, and then we do this JL transformation, and then we only store sign bit, that is 1 bit per dimension, and we use that to decode our original vector. So the total compressed output is 3.5 bits per dimension. And finally, we can see that TurboQuant is not a magic, but it's a geometry. So the main insight is random rotation distributes outlier energy across dimensions. And the second thing is polar coordinates eliminate the need of storing calibration overhead. And final thing is we have to store one residual bit which corrects the attention bias that we saw earlier. So all these things together gives us 6 times the memory, 8 times the speed, and zero accuracy loss. So this is a wonderful paper that's published by Google Research. So I'll be linking all the reference articles that I have used in this presentation. Please take a look at that. And thank you for taking time and watching till here. We'll meet you in the next video.